Can just someone tell me if it's visible? Is my screen visible to everyone?
Yes, Siddharth, it's visible.
All right. Yeah. All right. So coming back. So yesterday we left off at temperature, right? I was explaining you guys how temperature works in the context of LLMs and how it helps LLMs produce a different output every time you give it the same input, regardless of what the input is. Every time the LLM will give you a different output. That is because of a high temperature that's used in tandem with your softmax function. All right. So coming back. So today we'll be covering tokenization, right? All right. So to start off, I'll explain you tokenization and how the attention blocks, how they handle tokenization and how they absorb a contextually rich meaning in order to process the input that you give the LLM. So right, uh, if I just type type a quick sentence, wait, let me just zoom in over here. If I just type a quick sentence, uh, understanding tokenization is, did someone say something? All right. So let's say, I guess this has to be an S because this is Queen's English. What? All right. Never mind. So right. So understanding tokenization is important. So what if we input this into our LLM? This is our input into the LLM, and how the LLM is going to process this. Yesterday I told you that. Yesterday I told you something like it's gonna it's gonna create a vector embedding for each of these each of the just one sec. Right, I'm sorry. So right, it's gonna create a vector embedding for each of these tokens. And I told you that just for the scope of yesterday's lesson to refer to these entire blocks of words, this understanding, this tokenization is important, all of these as individual tokens. But what really is going under the hood, there are multiple types of tokenization strategies. Like, for instance, one sec. There are multiple tokenization strategies like BPE or byte, which stands for byte pair encoding, byte pair encoding. This one's BPE is used by, for examples of BP, we have ChatGPT. All right, GPT uses BP. And uh, then another technique that we have is this, let's just label this as one. Then another technique that we have is word piece. Now, word piece is used by BERT if you, uh, as you guys may have heard of BERT, and we're gonna cover BERT today as well. I have an exciting project to show you that will help you understand how BERT works, and we have third one. Another one that we may have is sentence piece. Okay, so now coming back to this, how this word is going to be broken down exactly is uh, now I'm going to consider BPE because it's the most widely used one out of all of these. And actually, what modern day LLMs really use is subword tokenization, but I'll just use BPE for the scope of this lesson used by GPT. So, all right, so it's gonna break this into first token will be under, then we're gonna have understand tokenization important is the input string. So we're gonna have this string broken down into under, then standing. These are tokens, individual tokens, by the way. Understanding. Then tokenization is going to be broken into token plus ization plus ization, and it's going to let is remain as is, and then lastly we have important. As you can see, important and is they are full, they are processed as full suffixes and etc. However, understanding can be broken down into a group of two words, under and standing, obviously, and tokenization. Ization is a suffix for token, so BP handles it that way. And so this way, our four-word input, four-word sentence, it becomes the tokenization length for it becomes 6 tokens. But honestly speaking, it's even more complex than that. For instance, some of these encoding strategies, they ignore white spaces. Okay, some of them ignore white spaces. White spaces, as in your space, ignore white spaces, but not all of them. For instance, uh, sentence piece sentence piece does not ignore white spaces. So tokenization techniques work really. Okay, so exceptions. First, let me quickly write the exception for this one. Then piece. All right. Okay. So firstly, we let's just start with word piece. I'll tell you what word piece is, which is used by BERT. And by the way, for those of you wondering, BERT stands for any of you that may be wondering, BERT stands for bi-directional encoder for bi-directional encoding. Encoder representations for transformers. This is not just a model, it's a type of architecture. BERT is a type of architecture developed by Google, and that's all you need to know about BERT. So yeah, BERT stands for bidirectional encoder representations for transformers. Did anyone say something? I think I heard someone. All right, I'll take that as a no. So coming back to word piece. Word piece basically it starts by uh, word piece essentially works like this only, like how I just split understanding tokenization is important. And what it does, it splits words into characters, right? It splits words into characters, and wait, uh, let me go back here instead. So word piece, how word piece works is it splits words into characters, and then merges. Then it merges the most frequent combination, most frequent combinations of these into creating subwords. For instance, we, like I just told you, understanding AI, understanding tokenization is going to process like U, N, N, D. All right, and it's going to merge all of these. It's going to merge all of these most common characters. It's going to merge all these common, frequently occurring combinations of characters to create subwords like under, like we have under. And then similarly for standing, it's going to do the same thing. And word piece is word piece is used by BERT, as I told you, and it's very helpful when it's trained in a singular language with which have like clear word boundaries. This is very effective only when you're using a singular language. Then we have byte pair encoding, which works exactly like how I just explained you, understanding tokenization. All right. Understanding tokenization in which under is one word, under is one token, standing is one token, token is one token, and ization is one token. So this is also a frequency-based approach, and it also iteratively merges the most frequent pairs of bytes and group of characters. And then finally, what we have is sentence piece. So let me just quickly come to sentence piece. Now, sentence piece is really effective. It's really effective when your scope goes beyond just a singular language. It's very suitable when you're dealing with multilingual applications. Let me just quickly write that down for your reference. Multilingual applications. Okay, so sentence piece is really effective. Sentence piece is really effective when you're dealing with these multilingual applications. And sentence piece basically it tokenizes directly from your raw text, and it does not use pre-tokenized words like in BP, like you're using under, standing, etc. It directly uses the raw text for tokenizing. And this is kind of a unsupervised text tokenizer. Okay. Just random things you should know. And right, one more thing. Unlike unlike other tokenization techniques, sentence piece preserves white spaces. Why does it preserve white spaces? Because uh, outside of English, there can be the positional encoding of a lot of words may change. For instance, uh, how to explain you? For instance, what if we have a sentence in English, like something like I don't, I don't want to pet it. So let's say this is our sentence in English. And the literal translation for this in French would be, if any one of you who want to tell me what the translation would be, go ahead. Je veux, je veux pas caresser ça. In this case, in this case, preserving white space information is very crucial because the direct position of all of these, your nouns and your different tokens is different in these languages, right? So in this case, like uh, you're saying want becomes want translates to were, and pet translates to caresse. So obviously, as you can see, the one sec. So obviously, as you can see, the positional encoding is changing for these words. That's why preserving white space information becomes crucial in multilingual applications. As you may know, last time I told you guys, those tokenize. I'll just go back to that one. The context size for popular LLMs, as we know, this one's for GPT-3 22048 is for GPT-3, and then we have Gemini has 1.1 million tokens, right? Mind-boggling 1 million tokens. In just a span of 3 years, we made a jump from 2K token size to 1 million tokens. And Claude 3.7 Sonnet has 200K tokens. Claude 4 just came a few days ago, and that has an even higher context window. I'm not sure how much it is though, because Claude Anthropic hasn't revealed the precise numbers yet. But yes, so these are the token sizes. All right. So now you guys have a high level understanding of how tokenization works, right? Now we're gonna apply tokenization, and we're gonna see how attention, attention changes the vector embeddings effect on vectors. So right. So now we're gonna cover attention and how these all of these vector embeddings that, as I told you, underneath all of these are just huge high dimensional vectors. A, B, C. Let's say these are vectors. All right. So these are all of these singular tokens. For instance, U and N. These are all in context of LLMs just high dimensional vectors. Okay. So how LLMs work now? I told you guys that last time there's an embedding matrix. There's an embedding matrix that that serves as a lookup table for all of these vectors, and the it all of it then gets passed on to a self attention layer. Self So this is your self-attention layer. And then we have MLP layer, obviously, but we are just going to talk about attention for now because MLP goes beyond the scope of this right now. Um, so self-attention. How does it work exactly? Let's say, uh, okay, let's say we have a sentence like a furious young man. Let me just type this instead because my writing is becoming too mushy. A furious young man walks into a garden. All right, so this is our sentence that gets tokenized. Okay, and right now I'm not gonna deal with the actual tokenization of it. I've already told you how it works, but let's say just all of these are individual tokens. So these are individual tokens, and they get passed into uh, the self-attention layer. What the self-attention layer does is basically, let's say, I told you like the purpose of attention is to pay more attention to the parts of words that the parts of a sentence that matter more. So and to basically give the entire sentence a contextually rich meaning, right? So we have a furious young, right? A furious young. A furious young, this describes this man, right? Your man is your noun, and the furious young serves as a description for the noun. So what happens during self-attention is basically what happens during self-attention is just one second. Let me quickly draw a table for you guys. So what is the sentence we have here? A furious, a furious. I think my handwriting is too big for this. Just one second. A furious, young man walks into a garden. All right, so this is a sentence, and now I'm going to explain you how attention works in the context of this sentence. So how it really is under the hood, these are all just matrices, right? Sorry, vectors. Now this gets multiplied. All of these individual tokens, they get multiplied by something called a query matrix. A query matrix. All of these get multiplied by something called a query matrix. And so what the query matrix then does is the query matrix basically imposes a set of questions on all of these words. For the scope of this conversation, we're just gonna limit ourselves to nouns like man. Okay, so in the case of this sentence, how the query matrix is going to work is basically it's gonna ask this man token is gonna ask a question that whether there is an adjective in front of it, and then furious and young are going to respond yes, right? They're going to respond yes, there is we are the adjectives in front of man. And then we're going to have Again, the same thing. Since this is a self-attention layer, okay, keep in mind I'm saying self-attention. This means the key and the query matrix. The key matrix I'm getting to in a bit, but the key and the query matrix are gonna contain the same vectors. Okay, so this is self-attention layer. And the key and query matrix are gonna contain the same vectors. So a furious young. Let me just type now. Young man walks into a garden. All right. So so what happens? This all of these get multiplied by the query matrix. They get multiplied, and all of these get multiplied by something called a key matrix. What happens is that the query matrix asks a question, and the key matrix responds. The response is not going to come over here in the query matrix. Actually, the spurious and young are not going to respond yes, just in the query matrix part, but it's going to come from here in the key matrix. In the key matrix, one sec. Yeah, in the key matrix, spurious and young are going to respond yes. And how it's represented is essentially, it's going to just tell you like, I'll just use circles to represent it instead. So this Furious and Young are gonna have really huge circles here for when they're describing man. Uh, almost I missed out on an important part. What happens is that these values for each key and query matrix, they're all multiplied with each other. So this key matrix gets multiplied with the query for every token and for every single token. And what happens in the case of this bound, this Furious and Young, the value for this product of key and query matrix turns out to be higher than uh, other tokens that affect man, since they are directly describe man, right? So in terms of AI, this would be put like something like Furious and Young attend. Furious and Young, these both tokens attend to the embedding. They attend to the embedding of man. So right. So that this thing right here is self-attention. All right. And we also have something like cross attention. Okay. Now cross attention in cross attention, what basically happens is in key and query matrix, you had the same tokens for key and query part of it, but in something like cross attention, in a cross attention block, what you have is the query is in one language. Okay, the query is in I want to pet it, and the key matrix is in French. Let's say, as we said before, je ne veux pas caresser ça. So this is so in this case, as you can see, this thing is called a cross attention. This is a cross attention block, and this is honestly you don't really have to stress about this. Although when attention was introduced in the 2017 paper by Google DeepMind researchers, they introduced the concept of cross attention first. Okay, they introduced the concept of cross attention because originally attention was just intended to improve Google's translation models. Earlier, Google used to use a state of the art LSTM model, LSTM, long short-term memory model for which is basically an advanced RNN model for translating text from one language to another. But since the advent of transformers, the task has become really efficient and really accurate, basically. And so that thing uses cross attention. Google Translate basically it uses cross attention. Okay, right. Does anyone have any questions till now? I think I'm moving way too fast. If anyone wants to ask something, please go ahead. All right, I'll take that as a no for now. So coming back, also one more thing, I the size of this attention matrix, this key, this attention matrix, the size of this, it's I told you guys this yesterday as well. The size of this is uh, the square of the context window. So the number of tokens, the LLM is going to look at simultaneously uh, is going to be squared when we have to compute the attention for it. So that's you. So you can see how exponentially the attention scales with respect to context window, right? So the computation required for for an attention block is equal to, or the literally the matrix, the size of the matrix of the attention block is equal to the square of the context window, context size. For instance, if we have a context size of 128, 128 is 2 to the power of 7, right? So 2 to the power of 14, and which is going to be equal to, let's take a small number instead. Wait, let's take it 64 instead. So if the size of the context window is just 64 tokens, then the computation, then the size of the key matrix would be 4096. 4096 would be the size of the attention matrix. All right, so that's enough math for now. And if any of you, so all right, now instead of just me explaining you all of these in a very boring fashion, let me help you actually visualize how attention works. And I am going to use a BERT model. All right, I'm going to use BERT in order to help you visualize this. And the specific model that I'm using in this case, BERT, is used to basically. Wait, let me just open. And okay, so let me just quickly activate which one. All right. So now yeah, I was there at BERT, right? I was on BERT. So in this case, how we're gonna work it out is the BERT, we're gonna omit one word from a sentence, and the BERT model is gonna help us predict what that masked word is. So this is essentially a masked language model that I am leveraging for the scope of this project. And uh, so we're gonna run this using Python mask.py. And now we have to input a text. Okay, so let me just enter a furious young And now I'm gonna enter the masked token here, which Bert is gonna help us predict. Okay. A furious young dash walks into a garden. So now we're gonna give it for Bert to compute. And here you can see Bert returns us these uh, outputs. Bert has given us three possible values for the token. And we have here a furious young man, a furious woman, a furious young woman, or a furious young girl walks into a garden. And we can also visualize the attention. As you can see, uh, we also have all these attention visualizations for your reference, and I'll just show it to you in 1 sec. So let's start at attention layer. There's one. There it goes. So let's just start with attention, right? So here you can see, uh, right now the attention block is learning. Okay, that's why the attention computation is very noisy. And by the way, CLS and SEP, CLS stands for classification. It marks the end, starting of a sentence, and SEP is the separator token, and it marks the end of this sentence. Okay, so we have here a furious young mask walks into a garden. All right. So now, right now, the attention visualization is very noisy for this one, right? We have a lot of these blocks, and it's very noisy. But as you will see now, as we go into the higher layers, the model is slowly learning what could be the possible values for mask. So as you can see, first in the first layer, Furious and Young don't really attend to mask, right? But in the right next layer, Furious and Young start attending to this the mask token. Since Furious and Young serve as a description for the mask token, right? Uh, they are adjectives for mask. And now here comes here comes the a more rigid visualization for you guys. And in this case, you'll see we have Furious attending to Young, which I think you guys understand why. And then Young attends to Mask. And similarly, we have a very beautiful looking visualization here. And now the block has really now the block knows the attention layer knows what it needs to know, and it's going to just proceed in a similar manner. And now you're just going to see all of these tokens attending to the classification and SEP token in order to compute uh, what the masked word might be. Okay, so these are all just layers in a single head of attention. These are all layers in a single head of attention. Their modern day LLMs use multi-headed attention. Uh, right now, we have only discussed single-headed attention, right? But modern day LLMs uses multi-headed attention, in which all these attention blocks are parallelized. All of this computation is parallelized. There are multiple attention blocks which are all parallelized and sent over to the next layer. That's MLP. So why do we need multi-headed attention? Okay, let's say we have a sentence like uh, we have a sentence that goes like driver, drunk driver crashed his car into the rider. All right. So in this case, let's say the first attention block helps us compute the embeddings um, that this drunk, the drunk may be affecting driver. It's gonna so in the first head of attention. Let's say the it helps us the attention block helps us understand and absorbs the contextual meaning from just this from just certain tokens. But this sentence also has a lot of implications, a lot of uh, other implications as well. For instance, after a crash, the car's state would change, right? After 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 this crash, the car state would change for obvious reasons. The car's gonna have windows broken. The car's gonna have tires punctured, or whatever happens, and the airbags are gonna pop up. So that's why, in order we need multi-headed attention to be able to absorb as much context from these sentences as we can, and that right there, that's how multi-headed attention works. And so all of these, so for instance, one block of attention is computing what effect drunk is going to have on the driver token. And then the next one computes how what the state of car is going to be after the crash. And the next one is going to see whether the divider has been damaged or not, and etc. All of this stuff. So that right there is multi-headed attention. And then let's come back. Let's actually come back to context window. Okay, let's come back to context window. If you guys, so how LLMs really work is that LLMs don't like naturally know that they are supposed to uh, act like chatbots. For instance, you're using Claude or GPT, Gemini, all of these, they don't naturally know how to act like, they do not know how to naturally act like chatbots. So there's something called a system prompt. There's something called a system prompts that's given to these LLMs that basically tells the LLM that they are a chatbot and they need to respond to the user as if they were a chatbot. So it sets up so that context, that thing is called a system prompt. If you guys want to see, then I'll just show you a system prompt. Claude's system prompt was leaked a few days ago. If you guys want to really see, here is the Claude 3.7 full system prompt. If you want to know, so this thing right here. This is the system prompt of this whole thing. This is the system prompt of Claude. Okay, and this basically sets up Claude as a AI assistant and tells tells a user that uh, and tells the LLM that it's supposed to act like a chatbot to a user, right? So coming back to the lesson. So in tokens, so this is our system prompt. So the context window, the context window includes the context window is not just limited to your input string. It includes the system prompt, the entire conversation history, the entire conversation history, your message, okay, your current prompt, your current message, as well as the space needed for the model's response. all of that is a part of your context window. So you need to be really careful when you're using LLMs, so that you do not exhaust the context window and you get truncated answer. I am sure you must have seen that Claude sometimes, cuts your conversation in between. Not exactly cut, but it refuses to give you answers after you exhaust a certain limit. Right. And ChatGPT is infamous for truncating answers and different, different context. There are a lot of different context window strategies. Like there is hard cutoff. Okay. Hard cutoff is just like ChatGPT cuts off answer answers when they exceed the context window. There's also a sliding window mechanism. Slide, and this is separate, by the way. This is right. So this sliding window, which basically keeps the recent context but drops the older parts. There's compression that helps models summarize older context, and there's sparse or selective attention. Sparse attention. I told you guys. I'm pretty sure I told you guys sparse attention yesterday, and just let me give you a quick reminder again. Sparse attention is basically used by really advanced models, especially research models, that that helps the model prioritize the more important parts of your conversation history, and that is also done via the use of LLMs. All right, so that's how these are the ways that models address truncation or when you exceed the context window. So uh, I guess that's all. Do you guys have any questions, or do you want me to explain something in more detail? Any part in more detail? No questions. Abhishek, can you take over for a minute?
Guys, if you have any doubts, you can write in the chat box, or you can unmute yourself and. Okay, so we have got a question over here, Siddhant.
All right. Single versus multi-headed attention means what? I'm pretty sure I covered it just now, but okay, let me explain it to you again. There are a lot of different things that you can absorb from a single sentence, right? I just told you there are a lot of different things that you can absorb from a single sentence. This drunk driver implies has a lot of implications, and this is just a single sentence. Your prompts are going to be much larger than this, right? You're going to give it a very lengthy prompt. For instance, when you're debugging your code has a lot of implications. In just the context of this sentence, a drunk driver crashed his car into a divider. This implies that okay, the driver had alcohol, okay, and it also implies that the car's condition was damaged. The car was damaged, and it also implies that the divider may have also been damaged, and it implies that the driver was speeding up or hallucinating or something along those lines. So to address all those implications, you need multi-headed attention. A single head of attention can suffice for prompts, for small prompts like these. But when you give it a really huge prompt, you need multi-headed attention to process it, to really absorb the context-rich meaning. And by the way, I think you're forgetting that you also have a system prompt. which is really huge. I just showed you Claude's system prompt, and it was really huge. And all of these LLMs, all of that is included in the context window. So that's why you need multi-headed attention.
Guys, if you have any more questions, you can write in the chat box right away, or you can unmute yourself as well.
I suppose we have no more questions.
Yeah.
Guys, if you have any doubt, please don't hesitate. These topics, the topics told today about tokenization will be very important for the projects as well. So the concept should be clear when we move forward to the projects part.
So I believe I've addressed everything now, and it was a great session. I wish it was more interactive, and I wished you guys asked more questions, but uh, I I loved today's session.
Thank you, Thank you, Siddharth. That was a great session.
Thank you so much,
Thank
Abhishek,
you
for
for
the
explaining
opportunity.
all the topics very in a very good manner. It was very knowledgeable.
Thank you so much, Abhishek.
Vedant, we have a question over here in the chat box.
Oh, how will we create project and summation?
I will
What do you
let you
mean
know
by
about that. Submission, he's meant. I think it's about
oh
submission, right? Yeah.
oh?
So for
I
that,
think yeah.
uh, continue, Siddharth.
No. I was just saying that I think Abhishek will be more suitable to answer that
Yeah,
question.
so for your project submission, creation, and there were doubts about the certificate of completion as well. So for that, if you check the curriculum, day 6 is regarding the hands-on project, and day 7 will be about reviews. So on day 6 and 7, we will cover the projects part. To submit, we will release a Google form where you'll have to submit it on your GitHub, public it, and you'll be asked to send the link of the repository or your GitHub profile on that Google form along with some other details. And accordingly, you all will get certificate for completion as well. And we are marking the attendance daily through the participants via screenshots. So you'll have to attend most of the sessions, minimum 4 sessions to avail the certificate as well. Like it's not like every time you can just go through the recorded lectures. You have to be there in the sessions as well. All right. I suppose there are no more doubts regarding anything.
Also, guys, we'll be sharing the Microsoft Learn course link soon in a couple of hours. So you should refer to that. It would be a great revision for the next upcoming tomorrow's class as well.
Yeah, for today's MS link and you can avail to badge for today as well. I suppose there's no more doubt, so we can end the session right here. Did you guys enjoy today's session as well? Any reviews? Anything?
You can DM us on WhatsApp, any of the group admins, and do please react us and please let us know the feedback as well.
I suppose we can end the session. Thank you, Siddharth. Thank you for such a great session.
Thank you,
Thank you so
everyone.
much, Abhishek, for the opportunity as well. All right.
All right. All right, everyone. I think we can end the meeting right now. Thank you.